So we're going to kind of wrap up talking about, hopefully, internal combustion engines. Get some cheap little lawnmower engines, take them apart. You can learn a lot. Rotate the crank through the cycle. Watch the valves open and close. It's great. It's easy. It's cheap. Where is the crankshaft? It's running up and down, right? It's a vertical, not horizontal crankshaft. If you have another engine, it may be a horizontal crankshaft, but for a typical lawnmower, because it's down connected to the blade, then it runs around, turns the blade. Here is the spark plug, right? Here is the head. You can unbolt that real easy. See the piston, see the valves. And the piston slides back and forth like that on an engine, right? I know we all don't need to be experts at small engines or aircraft or whatever, but as mechanical engineers, we shouldn't just say, oh, I'm sorry, I got a degree and 4 years of education, but I have no idea what a piston and a cylinder do or what does. You know what I mean? You should be able to handle a conversation. So I'm serious about that. Try and find some and take them apart. So you can have an inline 4, a V6. So this is just the description of the geometry of the cylinders. And there's 3 and 3. And the other one would be a V8. So this one has 1, 2, 3, 4 cylinders in a V form. These are the lifters down in here. In the block, you have a cam that runs below it. The lobes are pushing up on the lifters below. And the lifters then, this is a push rod that come up to the top. This is the head. You're going to flip it over. You can see the 2 valves right here per cylinder. See the spark plug per cylinder. Then there is a rocker mechanism on the poppet valve up at the top. And some of these valves look discolored a little bit compared to the others, right? And this one looks a little, how would you describe the color difference between this valve right here and that valve? And then this one and that one, this one and that one, and this one and that one. See, it's a little oranger. What do you think it's from? Higher temperature. Which valve do you think this one is? Exhaust. Flow around, it's always high temperature exhaust. So this larger valve, larger diameter, is the intake, and it's cooler running because it's always being enveloped by the stem and everything by the cooler intake. This is the block, that's the head. Let's talk about the bore, the stroke, the displacement volume, and the compression ratio. So here's an illustration of piston in the cylinder. It's going to go up and down. At the top, you're going to have valves. Let's just focus on one intake, one exhaust valve like that, okay? This piston in this location is at bottom dead center, and it's at top dead center. The distance from the top of the piston, that's called the stroke, S. It's also the distance from the center line out, the crank offset, twice the crank offset gives you the stroke. So it's related to that geometry. The bore is the inner diameter. We'll give it the symbol B. So if you went back here, it would be that is the bore, right? What's the difference between the diameter of the piston and the diameter of the cylinder? Well, one has to fit inside the other, but it's very tight and it's negligible difference. So we just have a number for the bore, okay? We know that the piston has to be a little smaller, but it has rings to seal it up. I've tried to color code this volume right here, slight green color. See that? That's the swept volume. That's the displacement volume. So when the piston goes up, that volume is the displacement is equal to the stroke times pi bore squared over 4. Now at the top dead center, you still have some volume. That's in the head. See, usually you have a hemispherical head shape. And so this volume at the top dead center is not 0. Volume at the top dead center, it's much, much less than the volume at the bottom dead center. And that gives us the compression ratio. The compression ratio, R, is the volume at bottom dead center divided by the volume at top dead center. A trapped amount of gas, you take it and you squeeze it and you go 10 to 1, where the ratio is you started with the volume of 10, it went to 1, or an 8 to 1. You started with a volume of 8 and you went to 1. So that's a compression ratio. So this volume at bottom dead center is the displacement volume plus the clearance volume, whatever symbol you want to use for the clearance volume. But I tried to color code that purple. I don't know if you can see it, but the volume clearance. The volume at top dead center, well, that's only the clearance volume. Here's a engine. It's in a Buick. It's a V6. You can see the number of spark plugs. 1, 2. Let me color code this red. 1, 2, 3, 4, 5, 6. It has a coil. That's a coil that fires 2 of them. A coil. So you can count the number of spark plugs. It's at a V configuration. And right here it tells you 3,800. It's the size. It's the total number of cylinders. So the volume, the displacement volume of the whole engine, the entire engine is 3,800 cc or 3.8 liter. I had a number of questions after the 9 o'clock class, so I thought I'd throw a slide in. Sometimes you'll find that an engine gets worn and then there's some failure. This is some scarring on the cylinder wall. Can you see that? And maybe that's in for a rebuild. Maybe this is the skirt of that piston and it's no good. So what will they do? They'll bore the block, come in here and take some metal off, and either put in an oversized piston, new pistons which are oversized slightly, not a lot, just a little. They don't want to take a lot of metal off. If you have too much scoring, you got to throw the block away. It's not rebuildable. Or they'll bore it and then re-sleeve it. They'll have an insert and then get brand new pistons, and they'll be the same size though. But if they actually bore it and oversize the pistons, you can increase your displacement volume slightly in your engine. Okay. Also for a head, what would you do if you wanted to change the compression ratio? Used to do this a lot. Now I think it's old school, right? What would you do? You would take and mill down the surface of that head, take some material off of it. Just enough, just a little. And then it would boost the compression ratio. All right. Notice that the pistons have little indentations to accept, it's so small a volume up there, these valves, so that they don't interfere. Some people have an interference engine, some a non-interference engine. Basically, if your timing chain goes out of whack, breaks, timing belt goes, then the pistons are moving not in time anymore. Right after it breaks, if you have an interference engine, they kiss and we have traumatic failure. You bend the valve typically, or you pop the piston. Or if you have a non-interference, you're lucky, they can just go and they won't hit. So when you do an analysis, an Otto cycle or a diesel cycle analysis, my preference is you do everything with constant specific heats. When you need to make a change in internal energy, it's C sub V delta T. Change in H, C sub P delta T. What about, why isn't it a function of P1 minus P2 also, some alpha or something, some constant? It's not. Internal energy of an ideal gas is a function of temperature only. The same is true for enthalpy. It's a function of temperature only. Hence, this very simple analytic expression. Changes in entropy, yeah, we could start with this one or that one, but we often have isentropic process, which means that change in S is 0, and when that change in S is 0, these boil down to some very simple relations. But it's not funny when these equations get applied to steam flow through highly irreversible processes, right? Ideal gas, isentropic process. You just can't take this equation and say, wow, I love it so much, let's start using it for wild applications. You just lose a lot of points on exams, okay? But these are all very powerful, and we'll use them today. Also, if you wanted to evaluate the specific heat of air for a cold air standard analysis around 300 K, there you go. But if you wanted to go to a higher temperature, you can get more accurate or evaluate those specific heats at elevated temperatures. It's available to you, but often just grab it at 300 Kelvin and away you go. The table, I'm getting less and less enthralled with because I think more and more students just sort of jump into the table and do it and then throw the numbers out and they don't know what they're doing. It becomes more abstract using this column of P sub R and V sub R for isentropic process, right? They kind of lose sight of what's going on. So I haven't given an exam problem in the last 3 years that required a student to use this table for an isentropic process. I haven't. And I'm not this semester either. Guarantee it. You don't need to use P sub R's and V sub R's out of table A22 this semester for any exam. Now, if you do want to do it for the homework, fine. If it requires it or it says it needs it, go ahead and do it, okay? Any comments on that? If you've done it, it's just very algorithmic and it's not very insightful. All right, let's jump on. Let's solve a problem. We have an Otto cycle. It operates where 95 kilopascal and 300 Kelvin are at the start of the compression stroke. And then it has a compression ratio of 9.5 and a maximum temperature of the cycle is 1100 Kelvin. On the basis of a cold air standard analysis using that value of C sub E, that value of C sub P, and if you do the ratio, K will be 1.40. Determine, and now there's a list of things. I recommend that you be able to sketch from memory the PV and the TS diagram for the Otto cycle. Strongly recommend that. So start large volume in state 1, compression stroke. That's the end state 2. Constant volume heat addition, state 3. Expansion, state 4, back to 1. Thank you. Yeah, yeah, I know. He graded for us last semester, and I think enrollments are up at least 20 or 30 students. So, yeah, so. No, it's not repeats. It's people wanting a degree. Yeah, a lot of students wanting a degree. And then on the TS diagram, you go 1 to 2 to 3 to 4, and then back to 1 again. Now, I make it look easy, but please master this, all right? And then make a table to help organize your calculations. The table should be what state it is. I know there's only 1, 2, 3, and 4, so it's a pretty simple table. Pressure in some units, probably the pressure in kilopascal. The temperature in some units, probably Kelvin. And if you want, you could put specific volume in meter cube per kilogram, but you could really leave that off. But it's helpful. It doesn't make sense to have U and H up here because we're going to just do changes in U and changes in H. All right? Now for steam, last chapter, yes, it was helpful to have U and H at that state, as well as X for quality, but we don't have that. Don't need it. Now, another table is good for processes to help organize your work. So process 1 to 2, process 2 to 3, process 3 to 4, process 4 to 1. And there you want to say, okay, what was the change in the internal energy? What was the Q and what was the W? And we'll have these in kilojoules per kilogram, kilojoules per kilogram, kilojoules per kilogram. Okay? All right, so let me try and help flush this out because you really will find to answer a lot of questions like all the way to thermal efficiency, you're going to have to fill in both of these tables. Now, some of the information's given. State 1, what's the pressure at state 1? 95 kilopascal. What's the temperature? 300. What's the other piece of information? They said the maximum temperature of the cycle is 1100 Kelvin. That's T3. So that's 1100 Kelvin. So we know 3 of those values in the table. At this point, could I get V1? Sure. How would you get V1? How would you get it? Use the ideal gas equation. So is RT divided by P. Okay, so we could run that number for this problem. I think that number for V1 is 0.9063 something. Again, you don't need to do V's, but it's sometimes helpful to do them. All right, now, what about the process from 1 to 2? Look at it. It's S is equal to a constant. It's isentropic compression, where you're going from this volume to that volume. So the volume at 1 divided by the volume at 2, is that the compression ratio? Is that our 9.5? It is. So in our analytic expressions, we would want maybe to calculate P2 is equal to P1 times V1 divided by V2 to the exponent K. It's an isentropic process, ideal gas, constant specific heats. Boom. And so you can calculate this pressure right here, and it comes out to be 2220.9. How about T2? Similar expression. T2 is equal to, maybe I should have given the more general equation. P2 over P1 is equal to, and then how about this one? T2 over T1 is equal to, you can do it with V1 over V2 to the K minus 1, or you could do it as P2 over P1 to the K minus 1 over K. And they'll all be consistent. You have 3 equations. They're all cousins, right? They're all related. Yes, sir?
How did you find the K?
Okay, the K is by definition the ratio of specific heat, C sub P over C sub V, and it's going to be 1.40. If you just take those 2 values. Also, if we jump back to our table, this table right here, I think these are the values that are being used. Is it 1.005 and at 0.781? And then they did the ratio for you. It's 1.40. They even got it to 400 at 300 Kelvin. All right. So this comes in at a temperature of 738.3. You just continue through the system now. What about state 3? What is the pressure at state 3? I should do the specific volume just so that it fills out the table. Okay, there's the specific volume. Notice that that specific volume, if you took the ratio of those specific volumes, you'll get the compression ratio 9.5. Okay. What about now for state 3? Use the ideal gas equation that P divided by PV divided by T is equal to a constant, PV divided by T. So at state 2 and at state 3, that's true. In state 2, specific volume and state 3, specific volume are the same. And so we find that P3 is equal to P2 times T3 over T2. So you use the ideal gas equation to solve for the the pressure at state 3. 3309.2. And then this specific volume is the same. And then it jumps back out to 0.9063 for the final specific volume. But what do we do to get the temperature and the pressure at state 4? It's S equal to a constant. So instead of compressing, we're expanding. And use the same equations, and you get 141.5 kilopascal and 447 Kelvin. So you get your pressures and temperatures. Good? Now we look at the first law for each of the processes, 1 to 2. So which term in this first line in the table is 0? The heat transfer. Isn't it adiabatic compression from 1 to 2? Q is 0. So then we recall that delta U is equal to Q minus W for each of the processes. For the first one, 1 to 2, Q is 0. So guess what work is? Negative delta U. What is delta U? Delta U is always C sub V delta T. So it's C sub V times T2 minus T1. So you just fill in this table, and you find that the change in internal energy is, actually it's 314.7. And the work is negative 314.7. Okay, let's take a look at the process 2 to 3. 2 to 3 is constant volume heating. So the work is 0, isn't it? Now, that means that Q is equal to delta U. The delta U is C sub V delta T. We know the two temperatures. So we find that it's 25.9.7, 25.9.7. Am I going too fast, or is it okay? All right. Now, for 3 to 4, you tell me. Q is 0. And we know then that W, sorry, I got it in the wrong column. That the W is negative delta U. So we know, let me write that out, that U4 minus U3 is equal to minus work 3 to 4. Did I write that right? And so when we calculate the change in the internal energy, it's just C sub V delta T. It'll be a negative 468.7, and it'll be 468.7. This is a positive workout. True? It's expansion work at high pressure. A lot of work out. This is a negative work indicating it's actually in. You have to compress. The piston, this is doing work on the system, which is the trapped amount of air, to compress it. All right. And then the last, 4 to 1, it's constant volume. Heat rejection, the amount of heat that's rejected is 105.5 and 105.5 heat removal. It doesn't look like it, does it? But what is the sum of the 4 numbers in the first column? It'll be 0. They look like 4 different numbers. They are. But if you sum them, they'll be 0. That's great. You don't have an error. This is a good way to check your work. The next one, what is the sum of the Q's? That's Q net. Q net in. What is the sum of it's the work net. And when you calculate, you'll find that Q net and work net, not only are they equal, but the numeric value is 154.2 kilojoules per kilogram. Yes, sir.
Those are both negative from 4 to 1.
Yes, that's right. From 2 to 3, delta U and Q are both positive, and 4 to 1, delta U and Q are negative. Yeah. Go slow. Be careful. Avoid errors. Then what you can do, we've answered the question, what's the temperature at the end of the compression stroke? True. That was T2. What's the peak temperature? P3. What is the net heat addition? The heat addition is only coming in the process 2 to 3, so it's Q 2 to 3. It's 260 or 259.7 kilojoules per kilogram. What is the net work for the cycle? That is the 154. And the ratio gives you the thermal efficiency, 154 divided by 259.7, and you get a thermal efficiency of 59.4%. Look good? Make sure you can do an Otto cycle. What's the probability, Professor, that an Otto cycle analysis problem will be on the next test or on the final test? I would say a 75% chance. It'll be on one of those exams. How about a diesel? About a 75% chance. And then what about a Brayton? About a 75% chance. So we got 3 major cycles in this chapter that you need to really know. Otto, diesel, Brayton. I don't like it when a student says, I studied the Otto, but not the diesel. And, you know what I mean? It's like, no, got to study the Otto, then do the diesel, then do the Brayton, okay? And do them all well. All right.
Are the efficiencies generally in the 60% range?
Yeah, and then there's an analytic expression for the efficiency that we'll derive, but not today. And it's 1 over the compression ratio to K minus 1. So as the compression ratio goes up, that's a pretty good compression ratio. It's close enough to 10. So you solve a couple of these problems, you get a sense, well, okay, yeah, that's about right for the thermal efficiency. Somebody says, how about we go back and we revisit that cold air standard analysis. Let's go and do a warm air standard analysis. One way you can do it is you could say, well, what's the average temperature of the gas throughout the cycle? You could say, well, the temperature started at 300 and this. If you just add these temperatures up and divide by 4, you get, it's an average temperature approximation of about 650 Kelvin. You could reevaluate C sub P and C sub V and K at that temperature, this average temperature, and it'll give you a better estimate of the thermal efficiency if you really had a 9.5 compression ratio. But we're neglecting friction and a lot of irreversibilities, okay? And it's really just a trapped amount of gas being heated and cooled, expanded and compressed, right? So it's really a simple model. You shouldn't think it's going to be close to the actual performance of your engine with a lot of friction and other things. But it will drop that that percent efficiency because it's a warm air analysis. So it won't be 59, it'll be like 50%. Let's do now the diesel cycle. How many people feel comfortable with the diesel cycle? Not enough hands are up. Okay, so let's just go through this process. I'll explain it. You have a compression ratio, but instead of stopping at maybe a 10 to 1, you go to 20 to 1. You mean 1 to 20, 20 to 1. It really is higher compression. So think about going smaller on the closer to the axis on the PV diagram. And so it's going to go up, higher pressure, higher temperature at state 2. State 2 will be a lot closer, higher pressure, higher temperature. Now, they don't have mixed the air fuel and bring it in, not in a diesel. What they do is have fuel injectors. They don't have a spark plug, they have a fuel injector. And so when it's got the top dead center in our model, the fuel injector starts spraying fuel in. The temperature is already above the self-ignition temperature of the fuel, it starts burning right away. And it starts expanding so it starts the power stroke. And it'll be a constant, they model it as a constant heat addition to state 3. Constant pressure heat addition. Why is that justified? Anyway, it's because the fuel is being sprayed in, it's burning as it's being sprayed in, and the piston's expanding, or the piston's coming down in the cylinder, okay? But then something cuts off. What cuts off? The fuel. So you're going to continue to expand, but you'd have no more heat added, and now it's back to isentropic, S equal to a constant expansion. So you had S equal to a constant compression, then you had heat addition, but the heat was not at constant volume like the Otto. It's now at constant pressure. That's the only difference. And you still have heat rejection at constant volume between states 4 and 1. See that? So that's our air standard type diesel cycle. Let's go ahead and sketch it out here. 1 to 2, 2 to 3, 3 to 4, 4 to 1. What's constant between 2 and 3? Pressure. What's constant between 4 and 1? Specific volume is constant. between 4 and 1. Okay? So the heat comes in 2 to 3, heat goes out 4 to 1. All right. Do the same thing once you got the cycle down. Walk through the first law, and a lot of times the first time through is I'll say which Q's are 0, which W's are 0. So for process 1 to 2, are any of those terms in the first law 0? For process 1 to 2. Q. It's adiabatic compression. Is work positive or negative? This work right here. It's negative. Now you have a negative in front of a negative. You have to deal with that. But it's negative work. Meaning that it's not work positive out. It's actually being compressed. The system is the gas. It's being compressed. Now how about process 2 to 3? Is Q 2 to 3 0? No. How about the work 2 to 3? Is that 0? Yeah, it was 0 for the Otto, but it's not 0 for the diesel. Now, is that work 2 to 3, is that equal to the integral of PdV? Is it our traditional boundary work? Yeah, it is. But guess what? That pressure is constant. Can it come outside that integral? And what we find is that this can be written as P3V3 minus P2V2 because it's constant pressure. Pressure at 2 is equal to pressure at 3. True? So I can stuff that right here and then take it to the other side of my equal sign, and I'll have U3 plus P3V3 minus U2 plus P2V2 equal to Q 2 to 3. Do you see that algebra? And what is the definition? Right here. That's H3. This is H2. So we find that with some manipulation, the first law for process 2 to 3 for the diesel cycle is Q 2 to 3 is equal to change in H. That throws students for a loop. What? How come it's not changing U? It's changing H. Well, that's the explanation because it incorporates boundary work. There is some expansion boundary work during the process 2 to 3. So, okay, we continue on. 3 to 4. Is Q 3 to 4 equal to 0? Yeah, that's right. And what about work 3 to 4? Is it positive or negative? It's positive. You know, I forgot to ask that question. The magnitude of the work 2 to 3. Is it positive or negative? Positive. It's positive workout. So now the last one, 4 to 1, constant volume heat rejection. Work 4 to 1, 0. And then when I have the sum here, this will give me the Q net, right? The sum of the Q's. There'll be only 2 non-zero Q's. There'll be a positive Q2 to 3 and a negative Q4 to 1. And I'll sum it up and it'll be the net Qn, Q net. And then I'll sum right here and there'll be 3 terms for the work. 2 will be positive, 1 will be negative. But when I'm done, this Q net better be equal to W net or I've made an error. Then the thermal efficiency is the net work out divided by the heat in. It only came in Q 2 to 3. I don't have time to solve this problem. So we'll stop.